So we're in section, for us, this is section 1.5. So we're combining functions. So before we get into the details here, what do you think we mean when we're saying we're combining functions? What might we be doing with functions to combine them? Possibly. So what do we use common denominators to do to functions? Reduce the fractions, or what else? Adding. Okay. So we have to add. If we want to add functions. So one way of combining them is to add. So that's one way we might combine a function. So thinking along those lines, what else might we do to functions to combine them? Multiply. I'm going to put that down. Multiply. What else? Subtract, the opposite of addition. And divide. So one way of combining functions is to do arithmetic. Do arithmetic with functions. I'm not going to go into a lot of detail with adding, subtracting, multiplying, and dividing. Everybody, we all have a really good idea of how to do that. I'm just going to put the basic rules up here. I'm not going to go into a lot of detail. But before I do that, can anybody think of why we might want to combine functions? Easier to graph. That works. Makes it, we don't, rather than a bunch of separate things, we just have one thing that we're working with. So it makes it easier to graph, easier to visualize. Anything else? So when we, for example, on the summer packet, when we found a common denominator and added those things together, not only to make it easier to graph, what else did it do with that function? Simplified it. It's less complicated. And what someone else said, another really good one. What did we use common denominators and adding to solve the equation? So we have our equation and we're set it equal to 0. Well, so adding, subtracting, multiplying, dividing might help us solve that equation. Where everything's separate, we're not sure how we would go about it, put it together to solve it. So that's another good reason why we might want to combine them. Anybody think of anything else? So y'all came up with really good ideas. Part of what we're doing when we're combining functions is taking these things that are more complicated, putting them together so they're simpler. Gives us another way of working with different pieces. Put those pieces together might make it easier to work with. Another reason that we're learning about combining functions, seeing how we combine functions, is because as we go forward, we might want to take the functions apart. We might want to uncombine them. So if we have an idea of how we do combine them, what the rules are, then it makes it easier to take them apart. So what's an example of when we take functions apart? It has to do with did someone say it? When we solved some of these things, what did we do with some of the functions when we were solving them? Find zeros. And when we find zeros, what do we do often with functions to find zeros? Factor. When we factor an equation, we're taking it apart. We're undoing the multiplication. So factoring is a way of undoing the combinations. So if we know how the rules work, we have some experience with how the functions combine, we get better at then taking them back apart when we need them. And you probably have heard it other times in learning math that when you get to calculus, you'll do this. I'll say it again. When you get to calculus, taking functions apart is an important tool to have. Undoing these combinations of functions is an important thing to be able to do. It's something that you end up doing a lot. So for combining functions, let me just write our basic rules. When we add, we have two functions. We're saying that f and g are functions. With overlapping domains. So they need to have their domains in common to combine them this way. So to add, the notation that you'll see often is f plus g of x is just f of x plus g of x. And we know how to add functions together. We're just combining like terms. Same thing for subtraction. F minus g of x, we're just subtracting. And then multiplying f times g. And then when we divide, and what do we have to be careful with on this last one? Huh? The sign. I think you're thinking of inequalities. What do we have to be careful of whenever we divide? What gives us a problem when we divide? Zero. So where do we not want a zero? On the bottom. So we're saying g of x not equal 0. We just have to be careful we're not dividing by 0. And that's how we do our arithmetic with functions. Not complicated, something that we did a bunch of that on the summer packet. So any questions on that before we move on? And there'll be a few homework problems that ask you to combine functions in different ways. All right, can anybody think of, so other than arithmetic, and this is where it gets a little more interesting, another way of combining functions, where we put functions together. So we're doing something with two different functions and putting them together. Let me give you a hint. When we evaluate a function, what's our everyday word for what we do with our number that we want to evaluate a function at? So if I have, for example, x squared, f of x, x squared plus 3x, and I want to evaluate at x equals 3. What do I do with x? Substitute, plug in. Okay? So when thinking of functions now, what other kind of combination can we do with functions? So we're given x, we're talking about a domain and a range, so definitely going to have to work with that. Substitution, so like, what are you thinking of with substitution? Okay, right. So like solving a system of equations. solving a system of equations, we get y equals something, and we plug that into the other equation for y. So substituting. Does anybody remember what we call that thing when we substitute an entire function in for variable? Composite functions or compositions. That's what we're looking for. So we're going to talk about compositions. And it's related to substitution or plugging in. So that's the other way we're going to talk about combining functions, and this is where it gets a little more interesting. We do compositions. And we're going to write our compositions, and this should look familiar. F of G. And we're plugging, this is saying f of g of x, we're plugging g into f. So this is f of g of x. So we're plugging in g into f. One thing that we have to be really careful with compositions, where it gets a little trickier, is the domain. And this relates back to what you were talking about with the domain. The domain of f of g is all x in the domain of g such that g of x is in the domain of f. And it really sounds more complicated than it really is. What it's telling us is we have to pay attention to the domain restrictions of g, and then take into consideration the domain restrictions of f. So I like to call g, if we write our composition this way, g is the inside function. We have to take into account the domain restrictions of the inside function, and then take into account the domain restrictions of the outside function. That's kind of how I make it. And we'll do an example of when that's important. So we have to, when we're making compositions, we have to take into account the domain restrictions of G. So let's do a couple of examples of making compositions, and then I want to do one example. Part of what we're going to practice doing today is undoing compositions. And that, again, is another important tool that we're going to need moving forward. So any questions on what we mean by a composition? Plugging a function into another function is what we're doing. So let's look at a couple of examples. So we'll do an easy one. F of x is x squared plus 2x. And g of x is 2x plus 1. We want to find f. We want to make the composition f of g of x. So Samuel, can you help us out?
You plug in 2x plus 1 for all the x's.
Okay, plug in 2x plus 1 for all the x's. So how would we start writing our composition?
It would be 2x plus 1 is 20 squared plus 2 times 20 is 2x.
Beautiful. Everybody see that? We're just plugging in g into f. And then we could expand this out and combine like terms. If we go through the steps, I'm not going to go through the entire thing, if I expand this, distribute, combine like terms, I get finally 4x squared plus 8x plus 3. And because both of these are polynomials, I don't have to worry about the domain with these at all. So that's an easy composition. How about g of f? What do I get there? Paul? Yeah? We do the opposite, right? F into the g, exactly. So how would we write that? Plus 1. So I'm just plugging in f into g. That one's a nice easy one. So we get 2x squared plus 4x plus 1. No worries about the domain here. So let's look at one where we do have to worry about the domain. Let's say that f of x equals 1 over x plus 2. And g of x equals the square root of x. Let's form f of g. So what's f of g going to be here? What do you think? Shuffling my cards here. What do you think, Leah? Okay, very nice. Now, because I have this fraction, I need to worry about my domain restrictions. So just looking at f of g, what would we say our domain restriction would be for f of g? It has to be positive because can't take the square root. So we're taking into account the domain restriction on g. So we can't take the square root of a negative number. So x has to be, and how do we write positive? Greater than or equal to, there we go. Greater than or equal to 0. And so there would be our domain restriction. What if I switched it around just slightly? What if I said f of x equals 1 over x minus 2 and g of x equals the square root of x? So I'd have the same composition, right? F of g equals 1 over square root of x minus 2. I would have an additional restriction, x greater than or equal to 0. And what else? X cannot equal 4. There we go. So I'd have an additional restriction there. So the x greater than or equal to 0 is the domain restriction on g, because when I'm thinking of a composition, I'm plugging the number into g first. So whatever g does to the number, I have to take that into consideration first. And then I'm plugging it into f, so then I have to take into account the domain restrictions of f. So I have to be careful with both of them. And where it gets tricky is, I'm going to switch a page. Anybody have questions on these two examples? Where it gets tricky is if we had something like, and I'm keeping it similar to our last example, 1 over x squared minus 2 and g of x equals the square root of x. So f of g here, how would I write f of g for this example? Can you help us out, Austin? Austin Craycraft. Right. Square root of x squared is x times 2. So if we just looked at f of g, what would we say the domain restriction of f of g is? X not equal to 2. But we're plugging our number into g first. So we still have to say x greater than or equal to 0. We're plugging our number into g first and then plugging it into x. Into f. I can't plug negative numbers into g, so I have to take into account the domain restriction of g before I look at the domain restriction of the composition. So we would say x has to be greater than or equal to 0 for this, and x can't equal 2, because we're making this composition. So that's where it gets a little tricky. So questions on that? All right, I just have one last thing to talk about. Let's undo a composition. So we want to find f and g such that f of g of x equals, I'm going to move this down to my other line, equals 1 over the square root of 3x plus 1. So we want to find two functions so that we put them together in a composition and they make this function 1 over 3x plus 1. Anybody see a way we do it? What do you think?
X equals square root of x and 2x is 3x
So f of x is 1 over the square root of x. So f is telling me to take whatever I get, take the square root and form the reciprocal. And g is 3x plus 1. Does everybody see how we did that? Is there another way we could do it? Anybody see another way? What do you think?
Could it be f of x equals 1 over x and g of x is better than 2?
Nice. That would work as well. So sometimes when we're undoing a composition, there are multiple answers. So if I make f of g here, I get the same composition. Undoing compositions is a really important tool that you'll develop, especially when you get into calculus. It's an important tool that you'll have to be able to recognize what the pieces of a composition are, so you can take those apart. So that's really all I had to talk about today. I just wanted to ask a couple of questions. So in your homework, you're going to be asked to form various combinations of functions in different ways. So if you're given the graph of f and g, and it says some graph on your page, and it says find f of g of 5 using these graphs. How would you go about doing that? So let me draw a hypothetical situation here. So just some function, and the problem says find f of g of 3. So here's x equals 3, so I have a point up here. So how would I go about figuring out the value of this composition? How would I evaluate this composition? What do you think?
Find the corresponding y value on the v,
So I'm going up here.
and then plug that into f, find that corresponding y value.
Right, so I find this, so say g of 3 is from my graph, let's say this is 10. G of 3 is 10, then I would take 10 and plug that into f and go over here and find f of 10. Perfect. So that's how I use my graph, how you can use your graph to evaluate a composition. If you're given, there are a couple of problems on your homework where you're given graphs of two functions, nice lines. So you have some, I just got a lot of questions about these the other day, so I just wanted to go over them first. So if we have graphed on So we have two graphs. This is f, and this graph is g. And I want you to sketch a graph of f plus g using the information on the graph of f and g. How would we go about sketching a graph of f plus g from this information? Anybody have an idea? They're all lines, so it makes it easy. No ideas? So what we're going to do for a problem like this is look at each point here. Because these are all lines, we have a nice relationship. When I add them or subtract them together, we're still going to get lines. So I just find the value of f plus g at the endpoint. So I find the y value here and the y value here and add them together. So whatever, say this is 3 and this is 5, f plus g at 0 would be 8 for these 2 points. And then I would look at the x, I would add them together here, and whatever these are, I would plot a point for, let's say that's x equals 5. So I go over here to x equals 5 and plot the point where these two are added together. And I don't know where it would be, they would probably be up here further, and connect those. And you just do that from point to point to point. Because they're all lines, when you add them together, you're going to get other lines, and they give you nice points to pick, so you just add them together and plot your points. So that was this particular problem. I think I got more questions on than any of the others on the homework yet. Okay, let me put your homework up, and then I will get the information for you to access the online textbook. It looks like more than it really is. There are a lot of graphs and that kind of thing, so it looks more daunting than it really is. quite a few people mostly finished by the end of class yesterday. All right, there it is.